So I'm going to go ahead and introduce myself, even though we still have 30 seconds to go. My name is Bob Jacobson. I have taught this class in years past, and Yury was called away, I guess unexpectedly, and asked me to cover for him. So I'll be your, I guess I can't say server. I'll be showing you the menu today, but he will be back on Tuesday. And I'm going to try to do it from the materials that he prepared. This is not entirely my style, and it might get a little bit rough at times. But we'll work with his slides, which are up here, and we're just going to go for it, okay? So we'll see how that turns out. The topic for today is both gravity and rotational motion from Chapter 3. And we want to start with gravity. Gravity, in the sense of the thing that makes the difference in the universe, is the single largest one. You're held together by electrical forces that hold your protons and electrons together in atoms, in molecules, in cells, etc. And that's relatively important for you. But the long-term structure, stars, planets, galaxies, and things that are bigger than that, is entirely dominated by gravity. Once you get much bigger than a molecule or a cell, electrical forces are not really nearly as important as gravity because it always pulls things together. Electricity, you can have positive and negative, and they can cancel out. That's why you don't feel a huge electrical force to your neighbor, but gravity doesn't work that way. So when you start having more and more mass, you end up with a lot of it. On Earth, you experience it as the force that attracts you toward the fore. You know, you all are definitely attracted toward the fore. You're standing on the fore. The people in New York are actually attracted in a slightly different direction because they're attracted toward the center of the Earth, and the Earth is round. The usual image is Australia, where everybody's standing upside down because they're attracted to the Earth from the bottom part of the planet. It's actually a little bit surprising how this works out. We know that more massive objects are heavier, that there's more force. If I think of this spring as just a scale, I have to pull on it harder and harder and harder, and it goes farther and farther down. So how far down it goes measures how much pull it needs to exert. Well, gravity on something like this exerts much more pull than gravity pulling on something smaller and less massive, not nearly as much pull. And large things like steel weights or several hundred kilo professors just sort of fall. They generate a huge amount of force. But regardless of that, you might think that the force of gravity on a heavier object would make it fall faster. There's a lot more force on this, and as soon as I let it go, that force is going to make it drop. But it's not the case. Everything falls at the same speed. Now, there's a slight caveat to that, which is that everything falls at the same speed if the only thing that's happening is that they're falling. The only important thing here, I'm not holding them up. Are they falling now? Why is this not falling? Because I'm holding it up. Why are you not falling, right? Why are you roughly 150, 200 students not screaming as you fall toward the center of the Earth? Well, some of you might not scream, but falling toward the center of the Earth. What's holding you up? Well, for 6 of you, it's your feet on the floor. For the rest of you, it's butts in seats, right? The seat is pushing up on you and canceling the force of gravity. The other thing that makes it not clear to people, that makes it not obvious that everything falls at the same speed, is air holding things up. What we have inside here is a little metal coin and a feather. And if I just allow them, I'm going to flip them up to the top, and then they'll fall. And maybe, hopefully, you can see that on the big screen, or you can see the red feather. But you see how long it takes? The coin goes thump, and it's at the bottom, and there's the feather. They're obviously not falling at the same speed. And the answer to that is that air is preventing the feather from falling. It's a little bit trickier than that, and we'll get to the details in a second. But if I pump the air out of this thing, this is just a piece of hose, and this is a pump for pumping air, which has no visible on switch. There we go. We'll just give it a second. After I valve it off and disconnect the hose so that I can flip the thing with no air inside it, what do you think will happen in terms of falling? Yeah, that's good. We'll turn this off. We'll close this valve so I can disconnect the hose and spin it. What do you think is going to happen? Right. The valve works the other way. Let's try that again. Now, let's try it. Okay, clearly I am not going to have a good day with the demos today. Once more into the breach. I'm going to let this pump for a minute while we talk. Make sure I get all the air out of it. Okay, close the valve. Hello, valve. Turn off the pump. Just for good luck, I'm going to leave the pump connected. And let's try it again. Excellent. Now we have a feather falling like a rock. Can you even see it fall? It just goes straight down. Okay, took a couple of tries. If I let the air back in, you maybe hear it hissing in, the feather falls. Not as fast. So why is it that these guys, these two heavy weights, fall at the same speed? The answer is their air resistance is insignificant. Their air resistance doesn't matter. The force of gravity is so much larger than their air resistance that they really fall at exactly the same speed, even though they have much different forces of gravity. That's because the more massive one, in addition to having more force, has more inertia. The extra inertia means even though I'm pulling on it harder, it won't accelerate as fast. And it's that balance between force and inertia that makes sure they all fall at the same speed. So everything falls at the same speed toward the Earth. We can put numbers on that. I'm looking for my laser pointer, which I have already lost. No, there it is. And in metric units, it's actually pretty easy to remember the number. It's 10 meters per second squared, or 32 feet per second squared. What does the 2 seconds mean? It's actually easier to think of it as 10 meters per second, or 32 feet per second, which is a speed, per second. As you fall, every second your velocity, your speed, gets bigger by 32 feet per second, about 20 miles an hour. So in the first second, well, you're stopped, but after a second, you're moving at 32 feet per second or 10 meters per second. After 2, you're moving twice that fast. After 3, you're moving 3 times that fast, et cetera. We'll show you some numbers on the next one. But the idea is that you're going to speed up. You'll be traveling faster and faster. And so over time, how far you go grows quadratically. If you go twice as long, twice as many seconds, you're going twice as fast when you hit the ground or when you get to wherever you're going, but you go 4 times as far in those 2 seconds. You've traveled for twice as long at twice the average speed. That's 2 times 2 is 4. So this quadratic growth can really catch up with you. Even small accelerations, if you leave them for long enough, can cover a lot of ground because you get up to a lot of speed eventually over a long time. A reminder that it's always pointed downward. This is actually a tricky bit, and it's a part that many people are surprised by. So I'm going to show it to you first, and then we'll talk about it. What I've got here are 2 identical balls and an apparatus that when I pull this string, we'll pull a pin out and we'll just drop this one. And you'll be able to hear it hit. I'll put the microphone down so you can hear it. This other ball is actually going to have a slightly different experience. It's going to get shot out exactly horizontally. So when I let this thing go, at the exact same instant that the pin comes out and drops this one will be fired. Now, that's pretty much what you'd expect it to do. We'll talk about this trajectory later on, but you wouldn't expect it to go straight. I'm not firing it out so fast that it goes and puts a hole in the door. I'm giving it some speed, and eventually gravity is going to take over and pull it down. If you watch cartoon physics, what it would do is it would get over here. It would notice that it was no longer connected to anything, and then it would fall. But, of course, you know that, A, the ball can't notice anything, and B, you have two things happening at once. You have, I threw it, but I'm no longer holding it up, so it'll fall. So the question for you you could guess what the question is going to be. Which one hits the ground first? If I launch them both at exactly the same time, which one hits the ground first? Well, there are three choices, right? This one hits the ground first because the only thing it has to do is fall. This one's distracted by traveling sideways. So it's, thinking hard. Or this one hits first because it's been thrown so much faster, it's moving faster. And moving faster gets you to your destination first. Or neither one of those, they hit at the same time. So think about it for like 5 seconds, and then I'm going to ask you to hold up one finger for the ball that goes straight down, 2 fingers for the ball that goes that way. Yeah, I know you guys got clickers, but I don't know how to work clickers. And 3 fingers for they both hit at the same time because we can't think of anything else. What do you think? You think about it for a second and hold them up. I'm seeing lots of 3s, but a few 2s and a few 1s. I have no idea what 4 is. 4, I think, is just, what would that be? The universe ends when we do this experiment. OK, so 3, 2, 1, drop. And you'll be able to hear whether they arrive at the same time or not, but you'll have to watch to see which one gets there first. Did you hear the clicks at exactly the same time? They land at exactly the same time. And the way to think about this is that they really are doing 2 completely independent things. They've got an up and down motion, which we would often call y or something like that. But they've got this motion, which is entirely given by gravity. And then this motion, which is completely perpendicular to this, is independent. The side to side, these don't affect each other. To be able to think about it that way really simplifies things a lot. I'll give you an example. I got involved in a question about the game of volleyball. In the game of volleyball, one of the things that happens is the ball comes to somebody on a side who needs to send it to his or her teammates, and there might be 3 people along the net. And they want it to arrive at that person so that person can just sort of slam the thing right down the throat of the other person on the other side of the thing. They want it to arrive at just the right moment. The teammate's going to jump up at the top of her extension and grab this thing. And it would be great if the other side didn't know which of the 3 people along the net were going to hit it. But one of them's very close to the person who's setting it up. Beep. And one of them's very far away. Beep. That takes a lot longer, right? But in fact, you can think about that trajectory of that volleyball as an up and a down and a sideways. And if you teach the person who's setting it up to always put it up 5 feet, so that it goes up 5 feet and comes down 5 feet, it'll take the same amount of time to do that if it comes back down right next door or if it goes way the hell over here. All that matters for how long it takes is the time it takes to rise up 5 feet and come 5 feet back down. Demonstrated with chalk. I want you to sort of count the time it takes for this to go up and back down in your head. Sort of a 2-beat, right? Thump, thump, thump. Maybe a 3-beat. Thump, thump, thump. Now I'm going to throw it onto the table so it rises up about the same height, but it goes way the hell over there. Thump, thump, thump. All that matters is the up and the down motion for the time it takes to rise up, losing speed, turn around and fall back down, is independent of how fast it's moving sideways. One of my favorite demos is this one. It's called The Monkey and the Hunter. let's see if we can apply this knowledge. The backstory is that there's a not very bright hunter with a cannon and a very bright monkey hanging from a branch. Right. And a teaching physicist who forgot to flip the on switch. On switch. Now, the hunter, being a not very bright hunter who hasn't taken Physics 10, aims the cannon where? Where would, if you hadn't thought about it, where would you aim the cannon? Well, duh, at the monkey, right? Can you see this laser spot on? He's sort of turned this way. You can't quite see the laser spot on him, but can you see it? There's a laser spot on the monkey. The monkey realizes that this is an undesirable outcome, and as soon as he hears the cannon fire, he's going to let go. Now, it's not a real monkey, in case you haven't figured that out, and we're doing this electrically. There's some wires here that as the ball leaves the cannon, the little magnet that he's hanging by will let him go. So we're going to fire it. At the moment that he hears it, he's going to let go. Where's the ball go? Does it go over his head? Because he let go and he fell. Does it go under him? Because, the ball's not going to go straight. It's going to take a long time to get over there. And in the time it takes to get over there, it will fall below it. The trajectory will be like this. Or will they hit? What do you think? One finger for the monkey gets below the ball. 2 fingers for they hit each other. 3 fingers for the monkey is the ball goes below the monkey. I'm seeing some 2s, seeing some 3s. Whoever it is with the 4. I don't know what it is with the 4. Okay, so let's try it. Those of you who think that they're going to hit, why do you think they're going to hit? Aside from the fact that why would we do the demo if they didn't? Right? That doesn't actually work when you're out hunting monkeys. Well, one way to think about it is the ball is going sideways, but what's it also doing? It's falling, right? If you were shot out of if you were a little ball and you were shot out of a cannon, your first reaction would be, I've been shot out of a cannon. And your second reaction would be, I'm falling, right? You'd experience both of those. The monkey is also falling. They're going to fall for the same amount of time. They'll fall the same distance. So we'll give it a shot. I never know whether it goes when I push it up or when I push it down. So it might be 1, 2, 3, 1, 2, 3. But 1, 2, 3. Yeah. 1, 2, 3. Okay, that didn't work. Just a sec. Okay. So for those of you over there, did it look like they went at the same height? Yeah, more or less. Okay, you're very kind. Now I got to find the ball. I had a spare one, but I lost it. Did you see where it went? Oh, thank you very much. Did it hit you? This is not the best hunting technology. Ouch. We'll take another try, and this time I'll try not to twist the cannon. I twisted it sideways by pushing too hard on the lever and missed it. But I don't want to have a smug monkey who thinks he can get away with these things. Well, he may have gotten away with it. There we go. Okay, one last try, just because I've made the scientific point, but really it's just too much fun not to do this. Wow, it's not even close to aimed at the monkey. Look at that. The laser spot is actually way up above him. There we go. Ready to try again? Yes. That was 3, 2, 1. That was much closer. And if we want to spend the rest of the day, we could probably hit the monkey several times, but let's move on. Okay, so everything falls. The falling has to do with just the vertical part of your motion, not the horizontal part of your motion. When we actually put some numbers on that, it's surprising how fast that fall will take you. When you're falling, you end up falling with some pretty fast speed. So in numbers that we sort of know how to go, if you fall from only 1 meter, 3 feet, you're already up to 10 miles an hour by the time you hit the ground. So you're used to the idea of jumping down 3 feet. That wouldn't really faze you to jump off a table like this. You'd think about it, for half a second, but it would be basically okay. By the time you get to 15 feet, that's 20 plus miles an hour. You'd think several times before you jumped out of a car at 20 miles an hour. And you'd think a couple of times before you jumped off something that was 15 feet high. You might actually do that. I'm not sure you'd do this. By the time you get to 100 meters, sort of Campanile scale, you're really moving when you hit the ground. These are the actual formulas, but this quadratic and square root dependence adds up to a lot of speed from not so much height. The other piece of this is that if you want to have combined motion, if you want to think about both sideways and vertical motion, you end up being able to predict quite a bit about that motion. So here, see, this goes on. Oops. What this thing does is it lets me run out of water. It lets me launch droplets of water in whatever direction I want to. So I can launch them exactly horizontal. This is an indicator that tells you the angle, and 0 degrees is exactly horizontal. And just like the ball that left that thing, they immediately start to fall. Or I could shoot them straight up, and they go up, and they come back down, and they go up, and they come back down. If I want it to go as far as possible, this is not the right answer. But you might think that the right answer is to send them sideways. But they don't go very far sideways because they immediately start dropping back down. We're throwing something from this level to this level. So what's the right answer? I need a little bit of up to get it to go somewhere. But if I have just a little bit of up, it's moving very fast in the horizontal, but it's still not spending very much time. It's not rising up and then falling down. These water droplets spend more time on their trip. This is the most because all the speed goes to upward. That's the longest that any individual drop can take. If you want to go furthest, 45 degrees is the right answer. Mathematically, you're using about square root of 2 for up and about square root of 2 for sideways, 70% up and 70% sideways. That actually works because of the way the velocities add. And that gets you the best combination of sideways speed and time of flight. You don't end up going nearly as high. The water will go up here about, let's see, that would be 45, so that's about 50 centimeters. Your highest point is not nearly as high because you've taken away some of the up speed to go sideways. And your sideways speed is not nearly as high. In terms of knocking somebody sideways, this is not nearly as good as shooting the thing straight sideways. But it's the best compromise with height. The shape of this looks vaguely circular, but it's not. If we had this gone, the water wouldn't continue around in a circle. It's actually the flattened out shape called a parabola. You may remember it from a high school geometry class or something like that. And mathematically, we can predict it very nicely. We don't have any problems with writing the equations that'll tell us how to do this for any given angle. It gets a little bit complicated if you're shooting up onto a cliff or you're firing something down. The simplest form is when it's at the same height, a baseball on a baseball field, or something like that. The actual details of this gets more complicated as you have to worry about, for example, air resistance on these little droplets. That'll make a big deal difference on this. 45 degrees is not actually the best angle to shoot out a golf ball or a baseball because air resistance will affect them at the end. And you want to defeat that with a little bit of extra speed, a little bit of a lower trajectory, because it's not going to fly for as long as you would otherwise think. But those are all things that people know how to do. So here we come to actually talking about air resistance and drag. And I want to show you something. Let me turn this off before I make an even bigger mess. Did that go off? Okay, that should be off. Yeah, okay, good. Like the feather, this is something that it's just a coffee filter. It's a very convenient standard shape. You can get hundreds of these, and they're all basically the same shape. Is this going to fall at the same speed as a piece of chalk? Well, I gave that away. It's got less mass, less weight, less downward force than a piece of chalk. This doesn't weigh very much. And it's got a huge amount of surface presented to the air compared to the piece of chalk. So this is going to make air resistance very big, and there's not a lot of weight to overcome it. Sort of majestic, right? What happens if I put a coin in it? What do you think? I'll take another one, and normally these all fall at about the same speed because they come out of the factory, they all weigh the same, they're all the same shape. I mean, they're practically scientific instruments. It's great. And when you're done, you can make coffee, which is even greater. Now, clearly, with the extra mass of the dime in it, it's going to fall faster. The question is why? Right? Right now, holding in my hand, at the instant that I let it go, it's going to have more gravity force pulling it downward. But everything falls at the same speed. How do I understand that this ends up going faster? Clearly, that's faster. And here's the answer. When this is moving very slowly, right now, barely moving at all, it doesn't generate a lot of air drag. And if I make it go faster and faster, it generates more. If you stick your hand out a car window at 2 miles an hour, you can feel the air, but it's not a lot of force. If you stick your hand out a car window at 100 miles an hour, you might not get your hand back because it's going to get slapped backwards into the window frame from the huge amount of air drag on it. So the air drag depends on how fast you're going. The faster you're going, the more a given shape, whether it be your hand or your car or your coffee filter, generates force, more and more drag force. So this thing starts, when I let it go, with some weight. But at the moment that I let it go, there's no drag because there's no motion. So there's force downwards. There's a total force or net force downwards. And it starts to fall, not just go down, but speed up. 32 feet per second. That means each second it's going faster. But as it goes faster and faster and faster, it generates more and more drag. And eventually it's going so fast that the drag and the weight balance, and it can't speed up. It can fall, but it won't fall any faster. It's got enough resistance that there's no force left over to make it fall faster. The speeds of these, this creates something called terminal speed or terminal velocity. You won't accelerate. An object that's dropping in a vacuum keeps going faster and faster and faster. But once you're in air and you reach the terminal speed for your mass and your shape, you don't go any faster. You just fall at that speed. Let's look at some. Now, I have now lost 2 laser pointers. Clearly, we need more laser pointers. Here's one. So the difference between a parachutist and a skydiver, you know what the difference between a parachutist and a skydiver is? Right? The skydiver is still hopeful. They both have the same amount of gravity force on them because they both have the same weight, but the parachutist has this huge parachute over the top, a lot more air drag. So the parachute doesn't have to go nearly as fast to balance the weight, the gravitational force, as this much smaller skydiver falling through the air. And the ping pong ball, which is very, very light, and the basketball, which is bigger and heavier, fall at different rates. A baseball is actually about the same weight as a basketball, but it's smaller, and so it falls much faster. This is why, for example, a mouse has no fear of falling. A mouse that falls from any height falls at a small enough rate that it can survive the contact. Cats are very close to that. They can fall from a great height, and if they land right, they're okay, and if they don't land right, they're not. That's why they get their feet under them. And people are not. If you fall from a high enough height, your terminal velocity is enough that you'll break bones. Horses will splash. I mean, they hit at a very high velocity. So the reason for this is called a scaling law. Think of a ball. If I make it twice as big, what happens to what it weighs? Well, it's twice by twice by twice. It's got 8 times the volume. I made it twice the radius or twice the diameter, but that makes the volume go twice this way, twice this way, twice this way. 8 times the volume, 8 times the weight. But how much area does it present to the wind? It's only presenting 4 times as much area to the wind, this way and this way. It's gotten much thicker, but that doesn't help. That doesn't create any drag. So all of a sudden, you've got a lot more weight and not enough more drag. The bigger an object is, the faster it's going to fall, all other things being equal. You can make them different shapes, like a parachute. You can make them different materials, et cetera. We can actually get a little bit more quantitative about this. This is 2 coffee filters. So the gravity force on this thing is going to be twice as much as the, I'm going to take my dime back. The gravity force on this one, which one's going to fall faster? The one with 2, right? That's this hand. Now, this is a little bit hard. I don't even know if you can get this on camera. Do you think this falls twice as fast as this? It's faster, but is it twice as fast? Well, if it is, I can release them from about half the height and all the height. If this is twice as fast, they should hit the ground at about the same time. Experiments where when you measure something hitting the ground at the same time can be very precise. So we'll see. Is that about 50-50? It'd be hard for me to hold a meter stick while doing this. But these are, this is about halfway. It's a little bit slower. It's not quite arriving at the exact same instant. Let's see if we can fix that. We could try 3, but I'm running a little bit behind schedule. Let's try 4. We got to get them to actually sit together, or they'll separate as they fall. Am I about 50-50? That's a little bit too much. I think I don't quite have them packed together right. Pretty close. See if I can pack them a little bit more. If you do this precisely and scientifically, you discover that this is another example of this quadratic growth. At speeds where air resistance really matters, your drag goes up as the square of your speed. If you double the speed, you have 4 times as much air drag. If you triple your speed, you have 9 times as much air drag. We needed 4 times as much force to double the speed of the thing falling. That's why, for example, there are speed limits that try to improve your gas mileage by having your cars go slower. If the drag was linear, if the drag was proportional to your speed, it wouldn't matter how fast you went to go to Disneyland. If you went faster, there'd be more drag, but it'd be for less time. If you went twice as fast, you'd need to run the engine twice as hard, but only for half as much time because you'd get there sooner, and it would be no different. But because air drag goes up as the square, you double the speed, you have four times as much drag. You need to run 4 times as much gas. Even though you get there in half the time, you've used 4 times as much gas per hour to do it. It's a net loss. So air drag is very hard to beat. You have to do things like changing your shape. You know, that piece of paper is obviously a bad shape if you want to reduce air drag. You want it to be more teardrop shape and pointy on one end. Pointy is always good. You want to reduce your size so you don't have to move as much air out of the way. There are things you can do to reduce air drag, but the quadratic nature of the speed is very hard to beat. Okay. So a big chunk of this part of the course, are you using Rich Muller's book? Yeah, he puts a lot of emphasis on this, are satellites. And satellites are actually pretty cool. They have many uses. The basic idea of a satellite is that gravity pointed always toward the center of the Earth gives you an opportunity. If I think of this piece of string as gravity, and I think of this as sort of the center of the Earth, if I can arrange everything right, I can get this kind of motion, which involves tangling myself in the microphone cord. Let's reach way out here and see if I can fall over backwards. Think about this for a second. This ball is moving in a circle. What's making it move in the circle? Well, I am, but how am I doing it? The string is what's pulling the ball to go around. If I cut the string, what will the ball do? It'll fly out and bonk somebody in the head. Hopefully not me. So the string is always, and at any given instant, it's pulling in a different direction. Right? Sometimes it's pulling from you toward me. Sometimes it's pulling from the door toward you. The ball has to be pulled in a different direction all the time. But gravity only points down. Well, this was worked out a long time ago. And the answer is, if this is the Earth, and here's a high mountain, and on the high mountain you put a cannon, and we launch from the cannon a cannonball, it'll execute a parabola. It'll go thump. All right, so this is maybe, the king on top of his mountain in his castle. He's bombarding the enemy villagers or something. If we do it a little bit more, it goes thump. And if you're shooting a cannon 12 miles, the Earth is big enough, it's close enough to flat, that down is in the same direction. It's actually not. I forgot to look up this number. I have it in my own lecture notes. But the two towers of the Golden Gate are something like 6.5 inches farther apart at the top than they are at the bottom, because they're vertical. And they're pointed toward the center of the Earth. And if you go a little bit sideways, the center of the Earth, that's the center of the Earth. The center of the Earth isn't 4,000 miles straight down. It's 4,000 miles straight down and 10 feet over. And that's a tiny little angle, but the bridge is big and the towers are tall, and it's a noticeable effect. If you fire it far enough, this starts to no longer be a parabola. It starts to be a different shape because gravity is pulling you in a different direction over here. And if you fire it really far, you miss. Putting something in orbit, if you think of it as being fired from a cannon, consists of firing it at the ground and missing. It continues to go sideways fast enough that as it falls, it just misses the Earth all the way around. It's still falling. It's still falling toward the center. If it wasn't falling, it would continue off in a direction like that. Now, Question, see how well you understand this. If I make it go even faster, what happens? I've fired it at just the right speed to go around the Earth at that height. And we're ignoring air resistance. We're assuming this mountain sticks up out of the atmosphere. If I fire it even faster, what happens? Well, if I fire it at just the right speed, I've got this big blue circle here, and he follows it around, and he comes back around. It stays at the same height, and it hits the cannon crew in the back after about 90 minutes. And this is probably undesirable. So actually, it's a little more complicated than that, because on a real Earth, the Earth would have revolved in the meantime and moved the mountain a little bit. But it would still come around at the same height. But if I do it even faster, let's pick another color. What's happening here? If I fire it so very fast that it has no time to fall, it's going to go in a straight line like this. So faster and faster, here, by the time it got to this white line, it had fallen this far. And the red one had had a chance to fall this far. One that's even faster takes less time to get here and follows. You can get longer and longer, higher and higher orbits. They all come back. They'll come back around through this same spot until you're firing it so fast that Earth's gravity doesn't bring it back. This one, drawn on a slightly different scale, here's a smaller Earth. Here's this red line that goes around very low. And here's the yellow line that goes around much higher, but eventually gravity gets it and brings it back. There are lots of different shapes for orbits. You can have, the red one is a very low and very fast one. The yellow one is called, for obvious reasons, elliptical. It can go much higher. You can also have orbits that are out here that are still circular, but are much higher up. Okay, well, that's not much for a circle, but you get the basic idea. The moon is in an orbit that's about 250,000 miles above the Earth. The lowest satellites are in an orbit that's about 100 miles above the Earth, but that's about 4,000 miles above the center, because you're really orbiting around the center. And so you can have different heights. How long does it take the moon to go around the Earth? Roughly. We call it a month, right? How long is a month? 29 days, more or less. So big orbits take a long time to go around. The lowest orbits are about 90 minutes. If you try to orbit in less than 90 minutes, you have a problem, because, for example, if you wanted an orbit that would get you around the Earth in 30 minutes, it would be here. And it's very hard to orbit inside the rock of the Earth. The rock gets in the way. So the fastest orbit is about 90 minutes. The moon is about 29 days. It's about 250,000 miles, approximately. The very lowest orbit is about 4,000 miles from the center, about 100 miles above the surface. And that's about 90 minutes. There's one in between which takes 24 hours, which is called geosynchronous orbit. It's about 24,000 miles up. It's a coincidence that it's 24,000 miles in 24 hours. In fact, those numbers are the same. It's just coincidence. You have to go really, really fast. Have any of you ever actually seen not just a rocket launch, but something that was going into orbit launch? You ever watched a space shuttle launch in person or anything like that? If you get a chance, I mean, you can't watch a space shuttle launch anymore, but if you get a chance to watch an orbital rocket launch, you should go see it, because it's a truly amazing experience. It's a huge amount of sound and fury and light and heat as the thing starts to lift off. What do you think it looks like after that? Is it something like the little water thing that shoots sort of straight up, and I want to give it enough speed to get it up to 100 miles or 200 miles? It turns out it's not like that at all. Almost as soon as they clear the tower, they start to turn over. And by the time it disappears, it's way over there, moving sideways at a very high rate. Because the amount of energy, of speed that it takes to get up to your altitude turns out to be very small compared to the speed that you have to go sideways so that you're in this orbit. You have to move very fast so that you can cover thousands of miles. If you're in a 100-mile orbit, you have to cover thousands of miles sideways to get the planet out of the way before you fall the height of your orbit. And you guys know who Felix Baumgartner is? Anybody know who Felix Baumgartner is? If you watched the Super Bowl, you saw him. Who is he? Yeah, he rode up in a balloon to 117,000 feet, something like that, which is about 20 miles. It's about, that's not space. 20 miles is only about a fifth of the way to an orbit, but it's, pretty high. His free fall is about half as long as it would take for a satellite to fall straight down if one were falling straight down, if you forgot to give it any sideways speed. And it took about 4.5 minutes. So a satellite, if you were to accidentally forget to make it go sideways, you just put it up there and dropped it, would hit the surface of the Earth in a few minutes. Sounds like a long time, but it has to cover a good chunk of the way around the planet in that time. That's why they move so fast. And this is the actual number, 8 kilometers a second, which is about 16 miles a second, in order for them to successfully navigate their way around the planet. So most of the rocket flight time to put something into orbit is going sideways to build up speed. And you've probably heard of Virgin Galactic, the thing that where you, for $250,000 you can ride up into space, and they say it's almost like being an astronaut. It's like 6% of being an astronaut, right? You've gotten half of the up because they don't actually get you to 100 miles, and none of the sideways to go into orbit. But it's still very, very cool. So if anybody wants to buy me a seat on one of those planes, there's my email address. I'd be happy to accept donations. OK, we don't do clickers, and this doesn't have to be a real quiz, but let's see if we understand what we've got. If you had a spy satellite, you'd probably want it to be pretty low down. You're probably not going to put it on the moon. Why is that? Well, you want to see well. And you probably can't see as well from 250,000 miles away as you can from 100 miles away. What? It's actually not hard to see 100 miles. The amount of atmosphere that you have to see, the atmosphere is sort of, if you packed it all down, it's about 5 miles worth of air. So if you look at San Francisco, that's like looking through the entire atmosphere in terms of how much blurring and things you'd get. And on a good day, if you go out in front of the Campanile, look through the Golden Gate, you can see the Farallon Islands. They're 80 miles out. They're 80 miles from Berkeley. So that's sort of the view that a spy satellite has. You can imagine with a big enough pair of binoculars, you could actually see something. It's not that far away. So the lowest down ones with good optics, expensive optics, can see reasonably well, but they have a certain amount of what's called dwell time. How long can they look? How long can they read what you're reading in the newspaper? Well, they can't read. A, nobody should be reading newspapers right now, and B, we're inside, so they can't see what you're doing. But if you were outside, how long could they watch you? Anybody want to? I suggest working it out. OK, fingers. 1, 2, 3, 4. I got 2s. I got 2s. I mostly got, there's a 3. I have no idea what 5 is. Are there 5 choices? No. 4. 2s. And mostly I'm seeing 2s. Why is 24 hours not right? That's like forever, right? So that would be that it was sitting there and watching you all day. And there are geosynchronous satellites. There are satellites that sit in one place in the sky. They're very high up. They're about 24,000 miles up. They're very convenient if you want to point a TV dish at them, because they don't move. They're always over your head 24 hours a day. As the Earth moves, the satellite moves with it, and they turn together, and they're always at the same point in the sky. But they're way high, and that's not where you would put a spy satellite. The right answer is about a minute. And here's the calculation. They're flying, this is actually done metric, but they're flying in about an hour and a half to go all the way around the Earth, 24,000 miles. If you prefer to remember it in English units, in miles, the Earth's about 24,000 miles around. The way to remember that is the equator moves at about 1,000 miles an hour, and it takes 24 hours to go around. So 24,000 miles. You're doing that in an hour and a half, so you're moving at about 16,000 miles an hour. I should be able to see you for a couple of hundred miles as I go by. That's going to be a small fraction of an hour. It's going to be about a minute. So it's going to be about a minute. What you may have seen on a TV show of somebody watching watching the villain for a really, really, really long time, not happening. In fact, the satellites that get the best view, you can actually see the perspective change as the thing goes over. You're looking at it from the side, and then you're looking at it from the top, and then you're looking at it from this side, and you're not looking at it at all. Okay. I don't quite know how much these things have been talked about in this class. We've talked about this universal law of gravity, which matters a lot. That comes mostly from Newton. Momentum and angular momentum are the other two things that really affect this a whole lot. This orbit, this yellow one with the very high thing, if you think about it for a second, in order to get into this orbit, we had to go faster. Even though we started at the same place, we gave this a lot more energy so that it was moving faster, it had more kinetic energy, so that it could go around. And it uses a lot of that up. It's moving quite slow up here because gravity has slowed it down, but it's still got enough sideways motion to continue around and fall. If you just look at the vertical part of that satellite's motion, if you just think about what it's doing vertically, it's doing something a lot like this, right? It's rising up, running out of vertical motion away from the Earth motion. It still has sideways motion. It's still going this way, sideways motion. It comes around. The concept of angular momentum is a little bit foreign to people. You've seen it, and because it's Winter Olympics time, I'm going to spend a little bit of time on it. I need a volunteer, because I'm old and fat and will blow this. I need a volunteer. It's a physics class. How bad can it be? Come on down. In the book, this demo is called the 3 dumbbells demo. What's your name? Casey. Hey, Casey. Thank you for doing this. Take a seat. Oh, thank you. So I want to talk about angular momentum. The concept of linear momentum, of moving in a straight line momentum, you're sort of used to. You have mass and you have speed, and if you're moving sideways, you'll sort of keep that until some force acts. But I'm going to spin you very slowly. Okay. This is a separate thing. This is called angular momentum, spinniness. And Casey will keep spinning until something exerts a torque or a twist on her. If there was friction in this shaft, that would be the twistiness, because the friction would slow her down. Or I can do it. I can put some force on it. I can make you go back the other way. I have to count your turns so I don't make you dizzy. Now, because it's ice skating season, let me show you another aspect of angular momentum. Angular momentum really starts to get tricky when you think about the fact that you can change where your mass is. You can do this. So Casey, I'm going to ask you to grab those by the handles and keep them relatively close. And then I'm going to, once I get you moving pretty quick, I'm going to ask you to put your hands out. You're already regretting volunteering, even though it was a physics class. Okay, stick your hands out. And bring them back in. It's the bringing in that freaks people out, right? The fact that you speed up by pulling these in without pushing on anything, without twisting. Okay, out. Okay, now just let them sort of sag out there. I want to get you up to a little bit more speed. And now pull them in. And now let them out. I'm going to stop you and send you around the other ways to undizify you. There you go. Okay, you got it? You okay? We're just going to, we got to give you 12 turns the other way. It seems counterintuitive, right? She can go faster. Normally, to go faster, you have to push on the ground, or someone has to push on you, or there needs to be some sort of external push. But what's happening is angular momentum is about mass, distance, and speed. Angular momentum is something that's way out here has a lot of angular momentum compared to something that's in here. So put them out. That'll slow you down. They're not moving as fast, but they're pretty far out. And now I'm just going to stop you. You okay?
I'm good.
Try standing up. You got it? Give Casey a hand. So, I mean, you'll see this in ice skaters at the Olympics, assuming anybody ever actually watches the Olympics. You'll see it in lots of different kinds of angular motion. I got a call to get the next demo warmed up. Give me just a sec here. You'll see it in lots of different kinds of motion where as something goes around, as it gets farther away in its circular motion, it'll go slower. And as it gets closer in, it'll go faster. So if we were to actually watch this satellite go around, close in, it's really whipping. And then it gets slower and slower, and then it falls. It goes really whipping, slower and slower. So we've talked a little bit about the idea of a geosynchronous satellite. Here's you, and there's the North Pole, and the Earth turns this way. And there's a geosynchronous satellite out here that's providing dish TV or something like that to you as it goes around. And you've got your little antenna hooked on this, and this has been put at just the right altitude, just the right height, so that it takes 24 hours to go around, and these two clock around. Now, this can't be quite right for us because we're not on the equator. Right? You know we're not on the equator, right? We might be the center of the universe, but we're not on the equator. So if you look at the Earth from the side, there's the pole, there's the equator, here's you. This satellite is way out here. Your satellite dish is actually pointed significantly south. It's not pointed straight up. It's pointed toward the south. Straight up would be this way. There's the center of the Earth. There's you. Your dish is pointed toward the south so that it's pointed at this satellite that goes around with you. In fact, there are people who live in parts of the world, my ancestors and everybody in Russia, who live so far north that this doesn't work. Their satellite dishes can't clear the bulge of the Earth to see. So they use a different kind of system. They use angular momentum. Here's an Earth. Here's their city. They have a satellite that goes like this. And they'll put a couple of them in this orbit. Here's one. Here's another one. Here's another one. They go way high up, halfway to the height of the moon, and they're moving so slowly when they get to the top that they just hang there for a long time. It's like that pop fly that goes up and you get like 30 seconds to think about the fact that you're not going to successfully catch it when it lands in right field. I'm speaking to the physics students in the audience. And they hang there for a long time because they're moving very slowly, like Casey's arms when they're farther out. And then they come back down and they spend a little bit of time here, but there's another satellite in the constellation, the group of three, up there at the top. So there are many ways to work these orbits. The other thing about angular momentum, in addition to conserving itself this way, I can be slow at a large distance, I can be fast at a small distance, conserving my magnitude, is that it also wants to conserve the direction of the spin. If we couldn't do it on this chair, but if we had tried to tilt Casey and have her rotating this way, the angular momentum would fight it. So this is an old gag from a TV show called Candid Camera. It's a suitcase. And it's just happily sitting like this. And if I just take the handle, there's nothing tricky about the handle, it's just a handle, and I try to turn it, it fights me. You don't really expect this behavior in a suitcase. It's really quite odd. If I want another volunteer to come down and play with it, we could certainly do that. What do you think's inside it? It's a great big aluminum wheel that's spinning. And to turn this, to make it go this way instead of this way, I'm trying to change the direction of the spin of this thing. And to do that, I have to torque it. I have to put some twist on it. But I have to put it in a direction that's completely unexpected. Three-dimensional angular momentum where you're trying to change the direction, is a quite complicated thing. It's one of the reasons that it took 40 years to figure out how to make helicopters fly after the airplane was invented, because they have this big spinny thing. And every time you tried to make the helicopter go one way or another by tilting the big spinny thing, it would behave in unexpected directions, and it was very hard to learn how to control those. So, okay, angular momentum is circular motion. If you don't have any torque, it's conserved, and you can mess with it because it's the product of the mass and the speed and this lever arm, this distance around a point. Okay, I've gotten a little bit out of order, but this is okay. We can make this work. When we talk about these satellites, we did already mention a little bit that the higher orbits, the ones that are like the moon at 250,000 miles, take a really long time. The lowest ones are 85 or 90. This 24-hour geostationary ones are 23,000 miles. They have to be over the equator. Like that. And in fact, the orbit over the equator is starting to get crowded. There are a lot of satellites up there. You have to work pretty hard to make sure they don't, not so much bump into each other. It's a big space. It's 24,000 miles big. But get so close to each other that when you put an antenna pointed at one, it's seeing another one too. You don't want the two TV stations to arrive at the same antenna at the same time. Where you launch matters. Why is that? Well, for two reasons. One is this is now another view of the Earth from the top. Here we are, and we're going to launch our satellite from here, and the Earth is going around this way. Which way is it easier to put a satellite into orbit? Let's see, we'll color code this. Maybe I can pull that off. I could launch one this way. Or I could launch one this way. Which one's going to take the bigger rocket? Well, the yellow one's got about 1,000-mile-an-hour head start because the Earth is turning in its direction. The red one, you're going to need enough of a rocket to counteract the motion of the Earth and gain back that in the other direction. 2,000 miles an hour is nothing to sneeze at. I've never gone 2,000 miles an hour. So we tend to launch rockets. Which way does the Earth turn? Does it turn toward the east or the west? Which way does the sun rise? Sun rises in the east because we're turning toward the east to see it. So we launch rockets toward the east. That's why American rockets for a long time were launched from the East Coast. They were launched from Virginia, or they were launched from Florida, eastward, out over the ocean. So there's also a launch site in Vandenberg, California, Vandenberg Air Force Base, which is like halfway between here and Los Angeles on the coast. Why would you, rockets launched from there are going to go west over California. And I'm not sure the Air Force cares, but it seems like an undesirable place to launch from. Why would you do that? Well, sometimes the orbit that you want to have is just whatever the easiest orbit you can get into. I want to launch a space station. The stupid thing is heavy. I need a lot of energy to get it up there. I want the easiest possible launch. So here's the globe. Oh boy, if I could draw, I'd be rich. I mean, that's not true, but I still can't draw. There's the United States. There's Florida. There's east. That's the easiest possible place to launch. Where does that satellite go? if I shoot it due east from there, what I've really done there's the axis, there's the equator, here's Florida, is I've launched the thing going that way. Right? And it can't stay there. You orbit around the center of the Earth. You don't orbit at this height. You orbit like this. So over time, this satellite will sort of spend a bunch of its time going around between the amount of north that Florida is and the amount of south that corresponds to that. And it'll eventually go over every part of the world in between those two. But that's the only place it'll go to. If I wanted to survey crops above Florida, if I wanted to launch a spy satellite, if I wanted to provide a scientific weather satellite, that's not going to do it because it's in an orbit that's actually very close to the equator. If I actually launched from the equator, the French satellites are launched from French Guiana, which is very close to the equator. They stay pretty much flat over the equator. They don't go very far north or south. The other kind of orbit is called a polar orbit. You launch from Vandenberg, and you actually have to go a little bit sideways to make up for the motion of the Earth, and they go like this. They go around the Earth this way. And they, even though they're going around like this, they still get to see the entire Earth because it's turning underneath it. So they'll be going around every 90 minutes. They'll be looking at one side of the planet and the other side of the planet and the other side of the planet and the other side. And we'll be turning underneath it. Every 12 hours, it'll get a chance to look at everything. This side will get it, and then that side will get it. And every 12 hours, you'll be able to see the same thing. So these are called, for obvious reasons, equatorial orbits. And what do you think the blue ones are called? Polar orbits. And the real rocket scientists have ways of making these exactly right. You can make a polar orbit that always goes over a spot at the same time of day. So you're always going over when the light is the same for taking pictures of crops, for example. You can make ones that adjust themselves. They move back and forth a little bit with the seasons so that you're always right near the line between sunset and sunrise, or sunset and daytime, which moves back and forth a little bit as the Earth goes around the orbit of the sun. There are various orbits you can build, but the basic structure is that you have to think about where you want your orbit to be based on what you want to do. And some take more energy than others. And the reason that we launch satellites from the east coast for equatorial orbits or from the west coast for polar orbits is just so that they can be launched over water. Because sometimes rockets don't make orbit. Sometimes they land in the water. And it's much better to land in the water than on a house or something like that. What happens to satellites eventually when they come down? Why do they sometimes come down? Actually, do they ever come down? I've got a question for you. This is actually a very neat question. I love this question. How do we know that the dinosaurs didn't have a civilization? You know about dinosaurs, right? Dinosaurs. You've all seen pictures of dinosaurs. You watch the movies about dinosaurs. The amount that we actually know about dinosaurs is very small. The number of skeletons we have is not that big. They've been in a sort of awful environment. The dinosaur bones are not actually bones. They're now rock that formed where the bones are. Any metal from that era would be long gone, would be decayed away. How do we know they didn't have a civilization? How do we know they didn't have cars, trains, iPods, stuff like that? You don't think an iPod would last 60 million years buried in muck? I don't think so. So how do you know? Well, I've heard 3 good answers to this. Maybe I'll hear a 4th one. Yeah, there'd be no oil because they would have used it all up. That's one of the good answers. The answer that I like is they didn't leave any satellites behind. They didn't have a civilization that was good enough to launch TV satellites. Maybe they didn't like TV. I mean, that's possible. The sociology of dinosaurs is not clear to me. But we know that nobody left geosynchronous satellites in Earth orbit. Low orbits decay. because low orbits are very close to the top of the atmosphere. And the lowest orbits don't last very long at all. There was a research satellite that was launched a few years ago to study the top of the atmosphere, and it was deliberately launched so as to only live for about 3 months before it came back down, because it was studying the very top edge of the atmosphere. But things like the space station require an occasional boost to raise their altitude back up as they lose energy to air drag. There's a little bit of air, even 100 miles up. But by the time you get to 500 or 1,000 or 24,000 miles, it takes millions of years for those satellites to come down. It's just the very lowest ones that lose energy and eventually fall. But what happens is, as they lose energy to, yes, he's tying all the parts of the lecture together, air drag, it's no longer on this red trajectory because it's no longer going quite fast enough. Instead of getting to here in a certain amount of time, it's only gotten to there, and it hasn't had enough time. It's fallen too far by the time it gets to something, and then it starts to get lower. And then it starts to fall further into the air, and that slows it down even more. And the difference between orbiting well and falling down is typically only a few days. Once this process starts, once you get into the atmosphere, it goes faster and faster and faster. It's hard to predict where the thing's going to hit because it's going all the way around in 90 minutes. So if your prediction of how much air drag it takes to stop it is only off by 45 minutes, you'll be all the way on the other side of the planet. So it's really hard to say, oh, okay, we're safe now. And you have no prediction capability at that level of precision when you're moving at 23,000 miles an hour. Oh, wrong slide. Well, 17,000, 18,000 miles an hour. Much faster than the speed of the Earth's rotation. Okay. Why are astronauts weightless? Are they actually weightless? Would I feel like I was not significantly overweight if I was on a spaceship? I certainly would not be thinking about my weight if I was on a spaceship. That would be like on the third page of things to think about on a spaceship. I'm not going to eat anything today because I feel very weightless. Imagine for a second that you're in Evans Hall, and you're on the way to a midterm exam in your math class on the 10th floor of Evans Hall. And you're riding up in the elevator. And due to a fluke of nature or a failure of engineering or something like this, just as you stop at the top, the cable breaks. And the elevator car starts to fall. Let's ignore air resistance, the safety measures. There are a lot of safety measures. We can talk about how they work. It's actually fascinating. But the thing starts to fall. What would your first reaction be? I don't have to take the midterm. Okay, what would your second reaction be? I'm falling. Okay, what would your third reaction be? I feel weightless. Because you're falling, and the cab around you is falling, and it's not pushing up on your feet anymore. If you go to Evans Hall, the FAR elevators, the Bechtel side elevators, are, as far as I know, the best elevators on campus for this. You get in the elevator on the 10th floor, you push the button, the doors close, and for a tenth of a second, you feel like you're falling. Because for a tenth of a second, it goes, whoosh, it really starts to drop fast. And it's not pushing up on your feet anymore. So what are you actually doing when the elevator starts down? You're falling. You're not falling as fast as this, but you're falling as fast as this, right? You're falling a little bit slower. It's pushing up on you, but not as much as it does to keep you still. Your weight is a little bit more than the elevator push, and you start to go downward. If it truly fell, that would be not a good ride for an elevator. Even if it stopped at the bottom, people would not do that. But anybody been on Tower of Terror at Disneyland or a similar ride? That's what they do. They just let it drop, and you feel weightless. So an astronaut inside this thing is doing exactly what the spaceship is doing. She's falling, and the spaceship is falling, and they're falling together. And because they're falling together, neither one of them is holding it up. This is an interesting demo. Would you please assure your colleagues that there is no top on that and it's full of water? Yeah, it really is water. There's no trick here. I'm going to use this in just a second, but I want to talk about it with the piece of chalk. If I just sort of go like this, holding a piece of chalk, what happens? Well, it depends a little bit about how I hold it and how fast I do it. This will be the last demo for today. If I go over the top slowly, at the top I still have to hold the piece of chalk up. Right? If I'm not holding the piece of chalk up, if I like wrap my hand around it and go like this, it falls. If I go really fast, what happens? Piece of chalk is not the best thing to do. A book or something heavy is better for this. If you go really fast, I actually have to pull the thing down, because this is how fast it falls. But if I'm going really fast, I want to actually pull it down faster than that. And to pull it down faster, I have to put my hand on top of it. So to go really fast, my fingers are above it. If I go really slow with my fingers above it, that's bad. I put my fingers underneath it. Oh, underneath it, I can go slow. But if I go really fast, well, that didn't work. If I go really fast with my fingers underneath it, it continues out straight that way because I didn't pull it down. It's a lot like these orbits. If we go really slow, it's going to fall. If we go really fast, it's going to go whipping out that way unless something pulls it in at just the right speed. So if I send this over my head really slow, what happens? Everybody cheers. Yeah, I know that. If I go really fast, it's going to be OK, right? How fast is really fast? It's not actually that fast. The problem is stopping. Starting is easy. You can get it up to speed in a half a turn. The problem is stopping without dropping it. It really is water. So why is this related to satellites and circular motion? Gravity only knows how to exert one force on an object. It's weight. And there's only one speed that a satellite can go around the Earth. I can't make a satellite that's 100 miles above the Earth go much faster by pulling on the string. That satellite is always going over at exactly the right speed. See, I'm not sure. Sometimes I can pull this off and sometimes I can't. It's always going over at the speed at which it's just falling. I did practice this, but it's surprisingly hard to get it right. The satellites are always going over at the speed at which everything is just falling at the same rate. And so that's weightlessness. They're not massless. They still have all their inertia. They're not weightless. They still have the force of gravity, but they're just all falling at the same speed. I'm going to leave to Yury talking about general relativity and black holes. But just as a predecessor for it, that's a picture of a black hole. And with that, thank you for listening. Yury will be back on Tuesday to get you back on track.